Good morning, everyone. Welcome to week 4 of our virtual classes. Please, if you can hear me, can you put it on the chat? Okay, thank you very much. So I believe everyone can hear me. And please, can you see my screen? Can you see my screen? Okay, thank you. Good. So, once again, you are welcome to University of Ibadan and to Chemistry Department, where we promise to offer you the best. So don't be scared. Like my colleague was telling you last week, you are in for the best experience. So don't let anyone premeditated fear fool you. And don't just walk by hearsay. Experience it yourself. And I know you have a very good experience. So I want to also believe that you are interacting with your LMS platform. I can see somebody saying he or she was having issues with LMS. Please, if you are such, the only people that can provide assistance at this time are our team at the technical departments. We call them items or MIS. They are available. I know you have done orientation, so you should have their links, but we will try and find out if there is a way we can send link to you on LMS. But if you go on the general page, I believe there will be the contact where you can reach them in case you have issues on how to interact with your LMS. And on our course platform, my colleague has gone ahead to give you your assignment, the first assignment. Please make sure you do it and submit before the deadline. Another thing is that for this particular week, I left a barcode linking to a video, an introductory video that I would have loved you to have watched before now. So I want to know, has anyone watched the video? Did you see the barcode? No, it's not the definition of acid. There is a barcode that if you scan with your camera, it will lead you to a document, a file that has 2 videos about atoms. Yes. Okay, thank you. I can see few people saying yes. Okay. If you see the barcode, God bless you. Okay, if you haven't watched it, please, I would like you to just go ahead and watch it. It's about introductory part of this particular class I'm going to be having today. Just introducing us to what atom is, the discovery of the atom, the atomic theory, Dalton's atomic theory, things you are familiar with from our secondary school days. So let's go directly to this class. And that's what you have: atoms, molecules, and intermolecular forces. It will be the introductory part of a whole topic. Now, just like my colleague said last week, like 6 or more lecturers are going to take this particular course, and everyone will focus on a particular topic. So this is the one I'm going to be focusing on. You know, when you have variety, at least it will spice up the environment, and I mean, just for the bigger the better. So our outline, and you can see I put condensed there because it's more than this. So what we are going to be briefly talking about is atomic nature of matter, Dalton's atomic and modern atomic theory, experimental evidence for atomic structure and atomic mass number, isotopes, relative atomic masses, electronic structure of the atom, energy level in atom, and the electronic configuration for now. Now, another thing I would like you to know is that I would like you to pay attention. Yeah, a short version of the class on the LMS pages so that you can go back and read, but it may not be as detailed as what you have in the class. So that's the essence of being in the class. So I would like you to please pay attention. Yes, you will have access to a short version of the slides. You will have access to it, but that will be at the end of the class, and hopefully before your test, the virtual test you're going to have. So let's move on to what we have today. So in the beginning, so talking about atoms, philosophers, those that think deeply, majorly people of Greece, the Greek, are very, you'll see a lot of ancient philosophers coming from Greek. One of them is Democritus, and he was the first person that, after deep thoughts, proposed that there is something that is the major backbone of any matter. When I say matter now, I'm talking of material thing. Material thing, that's the scope of science. Difference between science and other things. Science deals with material thing. Anything that has mass, like, occupies space, that's what we mean by matter this time around. Now, it's looking at any matter. It could be gaseous, it could be in solid form, it could be in liquid form. And you can see the time, the year is 400 BC. That's ancient. This is the way time is measured, at least to make us understand how far or early or close, the period we are talking about is. Like, we are here, we are in almost over 2000 AD. We are in over as we have over 2000 AD. So that is after death. I don't want to go into it doesn't have anything to do with religion, but that's the measurement of time that we work with anyway. So this is 400 BC. So it's so we are talking about something like 3,000 years or more ago. So that's when this happened. And that we are saying that at this time, this man thought deeply, and you can begin to imagine what level of technology, of exposure, of intelligence, of knowledge that was then. Very, very little. So it just thought about, like I said, philosophizing, thinking deeply. Many times these thoughts are not backed with experimental evidences, and that's what makes philosophy and science different. While science is focusing, or talking from the point of view of facts, figures that came through experimentation, formulation of hypothesis and theory. Philosophy is just based on critical assessment and thinking. Now, that's a part of science. Philosophy is a part of science in itself. We do that, but we don't end there. Philosophy ends in critical assessment, argumentation, thinking, but with no proof like experimentation. Now, so in his philosophy, in his thinking, he proposed, after studying a lot of things, looking at them critically, that if I take any matter and I keep breaking it down bit by bit, I will get to the tiniest bits of this particular matter that will still have the property that can still behave like the original matter, original material that I started from. And so the name he gave was a Greek name, indivisible, which is translated atomos in Greek. So that's where the word atom came from. So now I've talked about this particular philosophy versus science. So I need to know you that philosophy and science shares the tools of logic, conceptual analysis, rigorous argumentation, just like I said. But however, science, after observation, we go to experimentation, we go to reasoning, we go to formulation of hypotheses and theories. The critical thing about that is experimentation, such that what you say is not just a word of mouth. Somebody elsewhere can do what you say. I mean, try what you said and get the same results. Not to waste time about that, but you need to note this, because you may be asked the difference between philosophy and science. Now, moving forward, we now started having scientists. I mean, that now started from what was proposed, the proposition of the philosophers, and then test it out. Is it true? And from their experiment, one of the early scientists that worked on that proposal, which we call hypothesis, was John Dalton. You can see the year that they worked on it. And that means the philosopher came very much earlier before this. That was the philosophy that was on ground, that they met on ground. But now science started gradually, and then we can have all this. So from his experiments, from Dalton's experiments and the theory that came from it, theory is made when we have proven beyond reasonable doubts that the hypothesis is correct. We have proven beyond, so there is facts, there is figures. So one of those, and we have others, which are the basic, they come together to form the basic backbone of science. The principal laws of physics and chemistry comes from these theories. Number one, all elements are composed of tiny indivisible particles. They are called atoms. All these laws of multiple proportion, law of constant composition, law of conservation of material came from this. And I'm sure you are very familiar with this, but in case you are not, just look at them again. That atoms of the same element are identical. Atoms of one element is different from that of the other one. Atoms of different elements combine simple number ratio to form compounds. Because you can see the year, look at the year, the 1800s, 1766, that was when he was born. So let's say he was about 30 years or more before he came up with all this. So that's in the 1800s. That's when all this were formed. So even at that time, the knowledge, the exposure, the more as we know it now, was very, very limited. They don't have all the information. All this information that we have now, they had to source it out. They had to find it out. And I just want to digress and say that we also in this generation should not think there is nothing more to find, as if they have found everything for us. If these people were stagnant, they said, oh, this is it, we have it, there will be no progress in scientific discovery. And the reason why we have less or little scientific discovery than we used to have is because many of us are contented. They have found it for us, so let's just memorize and use what they have. If we have the opportunity to go deep into many of what we are using as scientific theories now, we are also able to find more, because knowledge has no end. So that's just telling you that you also, as you are, no matter, even as you are in 100 level, don't think you are just here to get to receive. You also should position yourself to be somebody that can give something, give knowledge, so you can know up to that level that you also would be able to give knowledge. Thank you. So moving forward now. So like I said, the theory forms the fundamental laws of chemistry, not only chemistry. So for example, that atoms can neither be created nor destroyed is law of conservation of mass or matter. That means what you start with, if you start with this, by the time you do a reaction and you get to the product, nothing is lost. That's why you have balanced equation. It's not as if you have 2 moles of hydrogen in your reactants and in the product you now have 1 mole of hydrogen. What happens to the other mole? Something is, there's no disappearance. It cannot just disappear. So there's a conservation of energy, conservation of matter, conservation of a mass. That's one fundamental, and it's not only in chemistry. It spans through all the basics, the physical sciences. Then the law of constant composition, that atoms of the same elements are identical and have the same mass and chemical properties. And law of multiple proportion, simple number ratio 1 to 2. That's what it means. Like H2O, CO2. That's the meaning of 1 of carbon, 2 of oxygen. Excuse me, 2 of hydrogen, 1 of oxygen. That's the meaning of multiple proportion. Now, while this looks good for a while, and that's the beauty of science, science is not stagnant. There is something that happens that we call a paradigm shift. When a new discovery is made from an existing discovery that makes the existing discovery insufficient to explain the phenomenon. Let me come again. There's what we call a paradigm shift. It is usual in all spheres of life, but in science, we have a paradigm shift when we have an existing theory, for example, and we now discover that there are more evidences that shows that this existing theory cannot sufficiently explain the phenomenon that is happening. So that's why we say we have a paradigm shift. And from this theory, which went for another, like over a century, we now have people that came with other theories. There are a lot of them. And those theories came from other observations that makes the Dalton's atomic theory, which was sufficient for a while to prove, to show that this is what is going on, which was better. Dalton's atomic theory was better than the philosophy, but it was not sufficient. After a while, there were evidences. So one thing science does is that it doesn't close eye to fact. Even though if the fact does not support your proposal, you don't close your eye. You don't pretend it's not there, because when you pretend that it's not there, that is what will cause problem later, even in the health sector, when people pretend that this is not happening. And that is why if you use a medicine now, they will tell you can report allergy. You don't want to assume that this medicine works very well and doesn't have a consequence, a side effect. So if somebody is asking me, is saying he doesn't understand what paradigm shift is. Thank you for helping me to write it down for him or her, and you can always seek clarification after the class. Thank you. So now we have what we call modern atomic theory. Modern atomic theory was not a work of just one person, as we will be seeing in a short while, how we came about some of this modern atomic theory. It was not the work of one person. So we cannot say this person's atomic theory. Like John Dalton's atomic theory was something that came out, and if the names were mentioned, most of them received a Nobel laureate for them. But this modern atomic theory were evidences garnered by several scientists all over now. So you have one in front of you. The atomic theory of Dalton says that all matter are made up of tiny indivisible particles or atoms. That means atoms is the last. When you break it down, you get to the smallest. That one say after atoms, you cannot divide further. But it has not been, with increase in knowledge, technology, science moving forward, because like I said, science is not stagnant, it's not stationary. So with increase in this knowledge, we have been able to see that inside the atoms, there are other tinier particles that can exist on their own. They can exist. So we call them subatomic. That means tinier than the atom. Some atomic particles, subatomic particles, and of course, you are familiar with electrons, you are familiar with protons, neutrons, positrons, mesons, and they are quite a lot. I actually highlighted electrons, protons, and neutrons because we'll focus a little bit about them in this topic, in this part of the course. We are going to be focusing a little bit on them. So you find that we can further divide atom. So because we can further divide atom, should we quench or set aside or destroy Dalton's atomic theory? No, but because we came from that theory to discover this. So we would rather say that an atom can be subdivided into subatomic particles. Let's look at the other part of the laws. The law of conservation, that you can neither create nor destroy atom or matter. Now, where this is true, but for the discovery of radioactivity, which is spontaneous emission from the nuclei, what we find inside the nucleus of some elements, not everyone. From there, you can actually create something new. You can actually create something new. And if you look at it, like I give the example of uranium going to thorium and helium. You don't find any uranium in the product again. Uranium has broken down into two different things. Unlike chemical, if it was chemical reaction, there's a difference between radioactive reactions and chemical reaction. If it was chemical reaction, if I have carbon and hydrogen in the reactant, they will go and rearrange in the product, but I will still have carbon and hydrogen somewhere in the product. That's what we mean. If I have potassium, for example, let's say acid and base, which we are very familiar with, HCl plus NaOH. If I have it in my reaction, in my reactant side, when I go to my product side, I'm going to have NaCl. I still have sodium, I still have my chloride or chlorine, and I still I'm going to have water. So all the elements, all the atoms of the elements that I have in my reactants, all of them are still going to be in the product. That's a normal chemical reaction. And that's what Dalton meant when he said atoms can neither be created nor destroyed. But here we find in radioactivity, new atoms being created from the nuclei of that radioactive emission of one. And then you have a radioactive substance. This is a gamma ray. What you see there, I don't know whether you can see my cursor. This is a gamma ray that is being given off. So I would advise those of you that are interested to please, for now, except if you have a question, I won't be able to look at the chat screen now, but I would advise that you concentrate on the slides and leave the slide and leave the chat. The reason why I have the chat on is to guide me in case maybe my network goes off. And I want to be sure whether you are hearing me or not. That's why I have my chat on. Otherwise, I can see some people are really busy with chatting, but this is not the time for it. And I also hope you know that each of your classes are recorded. And sometimes I used to wish I can play the recording and you can hear, like the person that was hollering at the beginning of the class before I muted everyone. It's recorded. And sometimes, like we say, this internet does not forget. So many of the things you are chatting is recorded. Your name is even there, it's there, as you are saying. So please, let's maintain decorum. Now let's look at the next theory and what we have as the modern atomic theory. It's talking about the same elements, having identical atoms of the same elements, being identical, having the same mass, chemical properties, and different from atoms of another element. Now, the existence of isotopes. Isotopy is when you have atoms of the same elements. It's the same elements, but you have different atoms of it. What makes them different? They can have the same atomic numbers, but they have different atomic masses. As we will know, you know already, but just to refresh your memory, you know that atomic numbers arise from the number of protons, which is usually equal to the number of electrons, because atoms must be electrically neutral. Protons are positively charged, while electrons are negatively charged. So if we have 8 protons, you are expecting to have 8 electrons to make your atom electrically neutral. Normally, atoms are electrically, all the atoms you find on the periodic table are electrically neutral atoms. So now, from isotopy was actually an offshoot of the study into neutrons. So you know that not only protons is present in the nucleus, we have the neutron. So we now find that even though the number of protons and electrons hit isotopy, but many of them, let me not say most, many of them exhibit isotopy. Okay. Okay. Sorry about that. That was why I can you hear me now? Hello? Okay, thank you. So that's actually why I kept my chat on my screen so that I can know when I will recap. I'm sorry about that. It's a fluctuation from my network. I'll quickly recap what I said. I was talking about isotopy. I said that the issue of isotopes came from as an offshoot of the discovery of the neutrons, I said it's not only the protons that were in the nucleus of an atom. It's not only protons. We also have the neutrons. So while protons and electrons remain the same, the number of neutrons of the atoms of the same element. What we mean by atoms of the same element, this is oxygen. You have oxygen in a cylinder. This oxygen will have a particular mass or volume, and this oxygen will be made, this particular sample of oxygen that you have is not going to be just one atom of oxygen. This oxygen that is inside this particular container, let's say I have 50 cm3. Oh, sorry, it's going to be measured in volume, not in volume of, not in solution. It will be measured in unit of pressure. So let's say we have a particular amount of oxygen in like a cylinder. In that particular container, we would have, like, let's say we have 1 billion atoms of oxygen inside it. Each of these atoms of oxygen, it will not just be, they will not have the same, each of the atoms will not have the same atomic number and atomic mass. That is what isotopes is all about. Some of them, all of the atoms will have 8 protons, 8 electrons to make the atom neutral. To make the atom neutral, you have the same number of protons and electrons, but the number of neutrons might be different. And that was why I said we have oxygen 16, oxygen 17, oxygen 18. And I was about saying that it's not only oxygen that exhibits isotopy. I said carbon also exhibits isotopy. Carbon, we have carbon 12, carbon 13. And this number that we wrote here is their atomic masses, which is a combination of the number. Is actually is supposed to be the measurement of their mass, but we write it in number form, because if we say we should be measuring the mass of proton, mass of neutron, we would have something ambiguous that will have decimal points, and that's why we use relative atomic mass. We relate it to a particular unit. That's what relative atomic means. Relative atomic, you use a reference, so you are measuring it with a particular reference. That's the meaning of relative atomic mass or relative atomic number. So this relative atomic mass is a combination of the atomic mass, the number of the protons and the neutrons. So because the neutron number is different, so you have, for oxygen 16, you have 8 protons, 8 neutrons. For oxygen 17, you have 8 protons, 9 neutrons. For oxygen 18, you have 8 protons, 10 neutrons. So hydrogen also exists, also have isotopy. It's not, we have hydrogen 1, which we normally call proton. We have deuterium, that's hydrogen 2, and we have tritium, that's hydrogen 3. So we have all this hydrogen. Chlorine, God bless you. Yes, you are good. That's good. So let's go to the next slide. So this one talks about the law of multiple proportion. That is, they combine in simple number ratio, because at that time when Dalton was performing this theory, it was a new knowledge, it was a new thing, it was a big news to be able to discover CO2, H2O, NH3, and so on and so forth. So these ones are, you can see, simple whole number ratio 1 to 2, 2 to 1, 1 to 3. At that time, they didn't have anything that is beyond, this this simple, they hardly have something that is combining in multiples of maybe 5, 6, and so on and so forth. But we all know, as time went on, that we have large molecules being formed, not only by carbon. Carbon has the ability to catenate, and catenation gives carbon the ability to form a large number, a very big molecule that has a long chain. So carbon to carbon to carbon to carbon, and so on and so forth. Sucrose is just a very small thing compared to the kind of giant molecules we have. We have serious giant molecules that are so big that their masses, you can Google, you can try to find that what is the mass of the largest molecule on Earth, and you can find, you'll be amazed, you'll be shocked. So now that makes this Dalton's atomic theory incompetent to explain the observation of the moment. And so we have that modern atomic theory. I believe we are good with that. So let's just take one or two more so that we can now go. Now, we'll focus on the first atomic theory that says that there is conservation, and where we are saying we now have subatomic particles. We will focus on it for a while, because that will lead us into the subatomic particles we need for this. There are many of us that will be going to other sciences. We also need electrons, protons, and neutrons. So those ones are the ones we are going to focus on. That part of the theory, we will focus on it a little bit. Now, there is a man, you can see, also around that 1870, that discovered the electron. Now, at those times when they make this discovery, it was just observation. It was later you will see that it was somebody else that gave the name electron. But this was the beginning of the discovery of electron. The man name is a scientist named Wilhelm Krupp, was doing an experiment. Now, this is the experiment that he was doing. As you can see, he was passing high voltage electric gas through various gases. Now, there were very few gases at those times. Oxygen, and there were very few elements. And it is not all the elements that were also gases. I hope you know. So we have hydrogen, fluorine. It's not, but some of them will exist as liquid. Some of them, like all the alkali metals, are existing as solid. Beg your pardon. Sorry about that. So the man Wilhelm Krupp passed high voltage of electric discharge through various gases. So when I mean various gases, we are talking about various elements, various atoms at low pressure. When they are at low pressure, that means there are fewer atoms. So he's trying to see, he wants to see what is happening to atoms in, he wants to see the reaction of electricity on, or charges on an atom. That was his own experiment. That was what he was doing. Then he now observed that when he did that, he observed a beam of rays coming out of the negative electrode as a cathode and hitting the positive electrode. He observed it for all the gases. It will change it from one gas to another gas. Well, and like I said, at that time, the gases were different elements, different atoms. Maybe he tried it with oxygen, he tried it with another element. And what he called it was cathode rays. Now, let me show you a picture of what he did. So you can see, this is what, so this is a tube, this is a tube, this is a cathode, we call it cathode ray tube now. You can, you've seen many animations of this. I will soon stop so that you can ask questions. I know I've talked for a while, because I can see some people are still chatting. Please concentrate on this class. Somebody is busy asking on NMS. Please concentrate. So please, let's concentrate. Maybe it's because you feel you are enjoying it so much. And okay, somebody is saying my audio is cracking. Is my audio cracking? Hello? Okay. Okay, thank you. Thank you. Okay, thank you. Okay, if it's not cracking, it will be network from either my side or your side. Okay, so now look at the cathode ray tube. You can see it has cathode, it has anode. And this was done in dark. There's a glass plate. There's a glass plate behind. So what you are seeing is passing electrical discharge through. There are atoms of gases. There are atoms of gases in this discharge tube, and you can see that when it passes it, it saw a ray. Now that ray, there are many things that were said about the ray, and that's I want to see if I can show you. I hope, I don't know whether you'll be able to see this video I want to show. I'll try and show it. Is my screen. I'm trying to share my screen. If it's not showing or if you cannot hear it, let me know.
Cathode ray tube.
Okay, no. So I'll stop sharing this. I want to share my other screen with you. So I want to be sure that you can see the video. I pray you'll be able to see it. I just pray you'll be able to see it. Okay.
Cathode ray tube.
Can you see? Okay. Can you see the screen?
Discovery. William Crookes discovered cathode rays when he was studying electrical discharge in gases, whereas J.J. Thomson discovered that the cathode ray consists of negatively charged particles called electrons. Production. Cathode rays are produced in a discharge tube. Hence, the discharge tube is generally referred to as the cathode ray tube. The cathode ray tube is a partially evacuated glass tube with cathode and anode placed at the ends of the tube. A vacuum pump is used to partially evacuate the tube. The cathode is connected to the power source with the help of a clip. The tube is supported on a stand. It was found that electric discharge through gases took place only when the pressure inside the tube is lowered, and the potential difference between the electrodes was high. To produce cathode rays, high potential difference of 10 kV to 20 kV is applied between the electrodes and the pressure is reduced to 0.0001 millimeter of mercury by means of a vacuum pump. A glow is seen on the walls of the glass tube. The bright fluorescence glow is due to the striking of the rays emitted by the cathode. These rays are cathode rays. Properties of cathode rays. Cathode rays travel in straight lines. When an opaque object is placed in the path of the cathode rays, a shadow is cast on the glass wall opposite to the cathode. This shows that cathode rays travel in straight lines. Cathode rays consist of negatively charged particles. The rays deflect towards the positive plate when the tube is exposed to an electric field. This is because the negatively charged particles in the cathode rays get attracted towards the positive plate. Cathode rays are deflected by the magnetic field. When the tube is exposed to a magnetic field, the cathode rays follow a curved path, showing that they are deflected by the magnetic field. Cathode rays produce X-rays when they impinge on a metal with a high atomic weight. Cathode rays travel with a high speed almost equal to the speed of the light and hence possess kinetic energy. When cathode rays are made to fall on a paddle wheel, the wheel starts rotating, showing that the rays possess kinetic energy.
Okay. Thank you very much. I hope, were you able to see that? I want to hear. Good. Were you able to hear? Very good. Thank you very much. So, for today, I would like to have, before we go, if we can, oh, beautiful. Thank you very much. So before we go ahead to do more, let me just round up the characteristics again, just for emphasis. I will just drop the characteristics of the cathode ray again for emphasis, because I know some of you were not listening. You were busy arguing about William Crook and J.J. Thomson. It's good for you. So, let me, I believe you can see my screen now. Can you? Hello? Okay, good. Thanks very much. So, now we are going to go, we are going for the, so you know, you are now familiar with the cathode ray, so I'm not going to sweat so much on the apparatus again. You have seen it live and direct. I mean, from that animation, you saw that we have a cathode and anode, and there is the atoms of the gases under low pressure were inside. Now, characteristics, this is very important. Please, pay attention to the crucial part, just for repetition's sake, that the cathode rays, because it was the observation that J.J. Thomson now took. It was from the observation that he made that helped in formulating a particular fact and figure about the cathode ray. So observation, you would lead you to inferences. Observation leads to inferences. So because this happened, then this is it. That's what observation. So what was the observation? The observation was, he sees rays. Now, what we saw now was not actually what he saw then. It's not going to be as clear as that. He would notice something, then he will keep trying to see, what is it? What is this thing that I'm noticing? So he noticed ray. And he noticed that this ray is coming from this side, going to that side. And one of the ways he knew is to put something in between the ray that he was seeing. So that's what, so when he put that thing, so that will tell you the source. It's like if the sun is coming from a particular side, your shadow will be on the other side of the sun. So that will help you to know where the sun is coming from. So one of the ways they knew where the source of that ray, whether it was from the cathode or the anode, was number one, to put something in front of it. So they now saw that the shadow was cast on the anode. So you can see that a metal cross was put there, and you see the shadow. And then to show that it is coming in a straight line. If it wasn't a straight line, the position of the shadow would not be where it is. So that shows it is put in a straight line. And that is, it is falling a bit, the rays is traveling on a straight line. That's number one thing that is important to you to note. The number two is that it possesses momentum and energy. How is that happen? They put something, a light paddle, a light, something that can rotate. I'm thinking of, this thing that children used to do, that they would put the cover of a bottle of a, you people don't drink from glass bottle like Coca-Cola glass bottle, that the cover of that glass bottle, not the pet one that you drink. In those days, one of the things that children do is they will punch it with a nail, hold it on a stick, and use it and just put it where there is air, so that it can rotate by itself just for fun. That's what we mean by like a pad, something that can rotate. And what makes that thing rotate is that air, something is hitting it. If it is by itself, it won't rotate. But if you put air, or just to show you that something is hitting it, something is passing energy to it. So that shows that cathode ray, for it to hit that thing, it has energy, it possesses momentum, and it's also a particle material. So you can see you can see that light well rotating. Then now, to show that it's another observation was to show that is it a neutral what is it? Is it a neutral charge or a charged particle? Is it neutral or charged? And it was shown by putting number one, the first thing they put there was a magnetic field. Electric and magnetic. I will show you the magnetic. See, this positive and negative plates are actually electric field. And you know that opposites attract. So if you can see the negatively charged, we don't call it electron at this stage, negatively charged ray is being deflected towards the positive plate. If it was a positively charged ray, it will be deflected towards the negative plate. If it was a neutral particle or ray, it will go directly undeflected. So this is to show that it's deflected. So that's what they noticed, that the ray was deflecting towards the positive plate. And it also deflects under a magnetic field too. Deflection under electric and magnetic fields shows, number one, that they are charged. And magnetic field will also confirm whether it is positive or negative, because anything that deflects towards positive in electric field will deflect towards the opposite direction in a magnetic field, to be in a magnetic field. And so other characteristics of the cathode ray is that they are independent of the material of the electrode. That is, whether you put this gas or that gas, that means they are inherent. It is not something that is happening in the gas alone, and in the glass tube, in the cathode ray tube. It is not because of the cathode ray tube that is happening. If you put another gas there, it happens. Then the material of the electrode, just to make sure that it is not the electrode that is playing games with us, and so on and so forth. So, like I said, I'm going to now, what I've said so far are the qualitative properties of the cathode ray, which we now call electrons. Like I said, quality. That means you can, but that's the fact. But science goes by facts and figures. So the next time we'll meet, we'll be talking about the quantitative, which was done by J.J. Thomson. So all you J.J. Thomson fans, now this is where we talk about your guy, J.J. Thomson. He was not the one that discovered the cathode ray, but he gave the quantitative description by working on what William Cook. Okay, so Now, this is where I end, and I'm waiting for your questions so that we can end the class. We have gone, so we have 5 minutes more. So I'm going to take 2 or 3 maximum because the time is almost up. So if you have questions, can I see your hands and I can help you, ask you to unmute. Okay, so everybody has questions now. So we start with Esther. Esther, let me ask Esther. Esther, I didn't want to know live, I'm right? I've asked you to unmute.
Yes, ma. Yes, ma. Can you hear me, ma?
I can hear you.
Yes, my first question is cathode ray and electrode. Can we call it the same thing, ma?
No, electrode is not electron. Cathode ray is electron. Electrode is different. We have electrode, we can have a positive electrode, a negative electrode, the cathode, the anode. So the cathode ray and the electrode are not the same.
Okay, but
But
cathode ray is same as electron.
Yeah.
Okay.
Electron.
Okay, so can we now say William Crook discovered the cathode ray while J.J. Thomson discovered the electron?
No. Somebody gave it a name. Doesn't mean it discovered it. Yeah, you are behaving like the people that discovered, they say they discovered Mungo Park that discovered River Niger.
Okay, so who discovered the electron, ma?
The person that discovered
Electron, ma.
I'm telling you, the person that discovered cathode ray, he may not, like I just said now, he gave us the quantity. He was the one that discovered what became the electron. Cathode, J.J. Thomson, in the next, maybe if you wait for the next class, you will see what J.J. Thomson, and he called it cathode, called it electron.
Okay. Secondly, ma, please, ma.
You see our question?
No, it's not a question. It's not a question, ma. Please, ma. The video you dropped during the class and the notes, please, can you drop it on the LMS portal so that I'll be able to watch it carefully and write down whatever I want to jot down from it, ma?
Well noted.
All right. Thank you very much, ma. Thank you, ma.
You're welcome. So please, so let's see. Olu. I'm not getting your name. I'm sorry. So I've asked you to unmute. I can't pronounce your name. O-H-U-N. Is it O-H or O-L? What's your name?
Ohuyo Michael, ma.
Okay. Ohuyo. Okay.
Yeah. I have 2 questions. My first one is I'd like to know the uses of cathode rays. Just 1 or 2. Like, what are they used for?
Now or then?
Like, just their uses, ma.
What is it? Cathode ray?
Yes,
ray? Or
yes,
cathode ray tube? Cathode ray is electron. So what is electron used for? We are talking about discovery of the electron. I hope you people are following me because I think it's like you people like story more than the science. So cathode ray is electron. What are electrons used for? He named it, okay, that's why I brought it down so low. I said this man, that's what he observed, and so that's the first name he gave it. He gave it the name, it's like you are doing something, you can improve on it later, but that's the first name he gave to it, cathode rays. So cathode rays are electrons.
All right, ma.
That's their name now. Yes.
Are there anode rays?
There are. We'll get to that. And actually, we have jumped to protons. So there are anode rays. So,
okay.
So thank you. Let's see Joseph. Joseph, the class is, we are supposed to end the class so that I've asked you on mute to, oh yeah, Joseph, it will be the last person.
Good morning, man.
Good morning.
I want to ask you, man, you said we are going to have a test earlier.
Yes.
How is the test going to be, man? Like, is it based on what you have just taught us, or
Okay. We always test you based on what we teach you and we think you should know. Because after we teach, we expect you to go, not just that. If you base it based on what we teach you alone. Now, teaching you and showing you, giving you the scheme of work like you normally do. That's what I the all the things you need to know in the work. I mean, should spur you to go and learn. I mean, read more about it. Go through the notes or the documents and the text we give, and then you are supposed to study based on
Yes, sir.
within that context, not outside it anyway. So that is where we would examine you. And the test, like my colleague said last week, is going to be done on LMS. Don't worry. When we get to that stage, we will tell you what you do. It will not be difficult. You are not going to be the first set to do it. So don't
Okay.
worry.
Thank you, ma'am. Thank you
You're
very much.
welcome. I'm
Yes.
afraid time is up. I know many people
Yes.
are already raising their hands up here and there. Okay, David, what's your question? Can I see David up? What's your question? I've asked you to unmute.
Okay. Good morning, ma. Are you
Yes,
hearing me, ma?
I can hear you.
Okay, ma. Ma, please, what's the difference between, is a cathode ray an alpha ray or beta ray?
No,
Because according to your slide,
no,
according to the slide,
no,
you say
don't.
that
No, the
cathode ray,
cathode ray is not alpha, is not beta. They are different things. They are different. A cathode
okay,
ray is not an alpha ray, is not a beta ray, it's not gamma ray. No. Okay. Thank you,
okay.
everyone. God bless you. See you next week. Now, this is not the end of it. Now, somebody was asking, is this the only course? I don't know about other courses. Every course has their own strategy. This is our own strategy. Now, I'm going to send you again. Please, if you have not watched that video, it says a little bit about what we are talking about. The barcode I sent, somebody was asking, I'll just point your camera on the barcode. Your phone will go to the link. It will take you to the site, and then you see two videos. The two videos together are like 7 minutes. They are not plenty. So 2 minutes for one, like 5 minutes for the other. Just a refreshing way to get you started. I believe you are all, I'm sorry for those of you, Bankole, Lanre, Debisi, John, Oshurin Made. I'm really sorry. I'm sorry that I couldn't take your questions. So see you next week when we tell you what to do for that. Bye, everyone.